Okay, I think I'm set off now. So, yeah, so thanks for the homeworks. I think you both handed in by email, right? Yeah. Okay, so any problems with the homework at all? No? Okay, so you don't want to go through any questions? Sure. Okay, all right. Then, in that case, then we can just kind of continue with where we left off last time, which is linear algebra. So, in this set, I'm talking a little bit more about sort of matrices, and just to recap a bit, there's various operations we can do on matrices, such as taking the transpose. This is where you invert the columns and the rows, so you just do a swap around this diagonal. So some matrices, special matrices are symmetric or antisymmetric. And you can also take a conjugate of a matrix, which just means taking a complex conjugate of the whole matrix. And you can have matrices that are real, that means all the elements are real, or all imaginary. And what's quite important in the context of quantum mechanics is this Hermitian conjugate, which is taking both the conjugate and the transpose. It doesn't matter what order you do that, actually, it gives the same result. And special matrices where, so this complex conjugate transpose is denoted by the symbol, which is a dagger. And this dagger, if it does nothing to the matrix, it's called Hermitian. And such matrices are actually important in quantum mechanics because it turns out that these are things which are related to actual physical observables. So anything that's like a physical observable, like position, momentum, energy, anything like this is always like Hermitian. So that kind of makes sense because you can't have imaginary, energy, and you can't have imaginary position or momentum. It sort of doesn't make sense. So if we have things which are Hermitian, then it sort of guarantees that they don't give funny complex values. Maybe this is where we got up to last time. So a pretty important type of matrix is the identity matrix. So it's kind of deceptively kind of simple, but there's a special matrix where if you just have ones along the diagonal and zeros everywhere else, then this is the so-called identity matrix. And matrices, things that do something to a vector normally, right? So you have a matrix and then you do the vector multiplying the matrix. Usually it turns into some other different vector. Right? But the identity matrix is a very special matrix because it doesn't matter what vector you have. If you do the matrix multiplication or you apply the identity onto the vector, it just always remains the same vector. And you think, well, that's obvious because it's got ones on the diagonal, of course, it's going to be like that. But actually the identity matrix is pretty, really kind of important in quantum mechanics because actually there's a kind of a trick that you use to do calculations, and another way of writing this identity matrix is in this form. So I think we discussed why this outer product is like a matrix last lecture. These are like the matrix elements of each one of these terms in the matrix, basically what that means is that it's something that will take a vector e2, well, okay, let me write it. So something like e2, if you do a matrix multiplication of that with any of these unit vectors, then it gives E2, because what happens is that this unit vector is you take the unit product of that one with this one. So this thing here is just, this is a number, but this is still a vector. And this number, because all these unit vectors, remember these E things are all like unit vectors. So here's like E1, here's E2, here's E3. I'm just drawing 3 dimensions, but you can have any number of dimensions, of course. This inner product, because these are all orthogonal to each other, if you have anything like E1, E2, or more generally, EI, EJ, basically, if this will be 0 if I is not the same as j, and if I is equal to j, as in if it's the same vector, because it's a unit vector, it's equal to 1, right? So basically, this thing will be either 0 if this j is not equal to 2, or it will just be equal to E2 if j is equal to 2 in this case, because this will give 1, and then this will just give E2. So this thing, acts, well, it is actually like an operator, and it returns these values here. So you can basically see that something like this identity, which is the sum over all Ej, J. So this identity matrix, because it's in matrix notation, it's the one where it's just ones along the diagonal, 0 everywhere else. It takes all these, you have these terms where essentially it's only going to be returning j if you've got j there to start with. Okay, so this looks kind of like nothing so incredible, but the thing that makes this special is the identity matrix special, which I haven't written up there, is that actually we'll do this a little bit more later, but the identity matrix is actually the identity matrix in any basis. So let's just look at a simple example of that. So here's, let's say I take these 2 unit vectors here, right? Now, suppose I take like a rotated coordinate system. So maybe I use different color. So let's say I've got another E1, I'll put an E1 dash on it, that's like pointing 45 degrees this way, and another E2 dash which is pointing sort of 45 degrees that way. Then say I've got E1 dash, so in this case this E1 dash is going to be, well, because, so here's, draw a triangle, this is a unit vector, this is also 1 because this is 45 degrees. So this one will be E1 plus E2, and E2 dash, just from the diagram, what will this be?
This is not
then, suppose I work out what the, so identity matrix is E1 and E2, right? This is what I just wrote over there. Now, suppose I work out what the identity matrix is for the E1 dashes, right? So this is a different basis. So you might expect that this could be different, right? Because it's a different vectors, definitions, right? But if I go and just substitute everything into here, so let me do that. So I'm going to basically put all the definitions into I dash. Then, so I'm going to get E1 plus E2 and E1 plus E2, but these are conjugate vectors, right? And for the E2 dashes, it's the same, but there's a minus sign here. So it's E1 plus E2, okay, E1 plus E2, okay. Okay, and then, so I can just sort of multiply this whole thing out. This is the good thing about working with this vector kind of bracket notation, because you just kind of multiply everything out, and then you can work everything out this way. So here we're going to get E1, 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 E1. Here we're going to get E1, E2. So actually this will be like an off-diagonal term. So this like this term would correspond to something like in this corner of the matrix. So it's a 2 by 2 matrix. E1, E2 would be something that takes E2, turns it into E1, right? Takes E2, turns it into E1. This is E2, E1, and this is E2, E2. Okay. Then, so that was just multiplying out this first one. And the second one is going to be very similar, except the signs are different. So this is minus, minus, so this is going to be plus. This one is E1, E2, but with a minus sign. This is E2, E1 with a minus sign. This is E2, E2, but with a plus sign. So you can see that these terms cancel out. And this one and this one are the same, so there'll be a factor of 2, but then there's a half. So actually this is E1, E1, and here you've got E2, E2. And so this is actually the same as I. So I started with I dash, but actually it's the same as I. Okay, so that was just a simple example. I could have taken any angle here actually, and this I would still give the same result. So there's a special kind of property of this matrix. It basically doesn't matter what basis, what coordinate system you take. It's the same matrix. This is not always true. If you took some other matrix, it would normally turn into a different matrix, because obviously, just like a vector, if you rotate your head, it looks different. A matrix also will look different if you rotate your head. So, yeah, okay, that makes sense. Mm-hmm. All right, so that's identity matrix, and well, I'll show you later, but later on in the course. But basically, this is probably the number one most used trick in doing some calculations in quantum mechanics. Because often you do stuff like rotating bases and doing funny things like this, and then the biggest trick that everybody does is do something like, say you're calculating some vector, and there's a bunch of matrices, A, B, C, and then what basically, the trick trick that everybody does is that you go, okay, I'm just going to put in a factor of I here, and of course that doesn't do anything. You know that I never does anything, but by putting in this factor of I, it often simplifies calculations, and so it's the golden trick of quantum mechanics. Okay, but we'll talk about that later. Okay, so so addition and multiplication of operators. So this is what happens when you've got like two operators. So two operators, well, you can, just like vectors, you can add vectors or kind of multiply vectors. In a similar way, you can sort of add or multiply operators or matrices. Same thing in this context. So all these matrices and all the algebra, well, the whole thing. We're doing linear algebra, right? So the whole thing is linear, right? So that basically means we can add the matrices first, or we could apply them individually on the vectors, add them, always gives the same result because it's linear, because we're doing linear algebra. But if we are consecutively applying matrices, in this case, well, firstly, say you've got this original vector alpha, and then say firstly you apply t to it, and then you get alpha dash, and then later say you apply s to it after you apply t, then of course we take the result from here and then apply it there, then the final result is alpha prime prime. So we can work that out either by doing it just as I described. So we take the vector, apply it to t, we get new result, apply that to s, do that. Or, of course, we could actually multiply the two matrices first. So we could just get like this combined S and T matrix, and then work that out. Then, kind of view this whole thing here as like a single operator. And then we could just think of putting in A to that and then getting the final result. So both of those things give the same result. But one thing that's a little bit different to the addition, where it sort of didn't really matter kind of, what order or anything here, is that applying operators or multiplying them in this way, matrix multiplication, it doesn't matter which order you do the t or the s. So if I did s first and then t, in general, I would get a different result to doing t first and then s. You can see this things like I think rotation, right? So if you're on the world here, so we're sitting on the Earth, and then you did some rotation where, so let me just put a marker here. So if you did a rotation around z axis, and then later on you did a rotation around the, say, x axis, like this way. In general, I think that should give a different result if you did that in reverse order. So z, I think you'd go this way, and x you'd end up around about there. Or x, okay, I don't know for this example. It looks kind of similar, but I think in general it won't give you exactly the same place. So I don't know. You can play around with that in your mind. But yeah, so rotations are things where you cannot change the order of them. So a kind of a measure, or you might think of like the degree to which the order matters kind of quantity called a commutator. Did you guys encounter? I don't know. I'm not quite sure what you learn in maths and what you learn. What you learn in physics and maths is slightly different. But this thing comes up a lot. Do you learn commutators, things like that? No. Okay. So commutators, again, it's quite important in quantum mechanics, but it's kind of the degree to which these things are different, right? So, I've said that doing t first and then s, so remember, your vector is going to be hitting kind of from the right here, right? So st means that t happens first before s. This guy means that s happens before t, apply s before t. And then so if I've said that these things are not necessarily the same, so the commutator is simply a difference of these things. And this will be another matrix. And if it happens to be like the zero matrix, then actually you can replace the order, because obviously if st is, well, st minus ts, so s comma t, brackets, that's a commutator. Definition of that st minus ts, and if that's of course equal to 0, then of course st is equal to ts, and it doesn't matter what order you apply these two matrices. But generally, it will not be equal to 0, it will be some matrix, some kind of matrix. And that matrix gives you sort of an idea of what the difference is between these two orders of applying it.
And is it possible that st and ts are not the same size? So they cannot do the operation?
No, I think they have to be the same size, yeah. Like, you're talking about the dimensions of the matrix. Yes. Yeah, so I think whenever we talk about matrix multiplication or anything, I'm kind of, well, assuming that it's going to be in the same space. Right? Yeah. Well, okay. Well, okay, so let's have an example of something that, let's erase one. Okay, so my example there wasn't really clear, so so this is the classic example of matrices that don't commute. So we'll encounter these matrices over and over again. But there's the so-called X matrix and the so-called Z matrix. So if I multiply X and Z, then, don't rewrite it. Okay, so we do the matrix multiplication. This will be 0. This guy will be minus 1. This guy will be 1. And this guy will be 0. Okay, so that's that matrix. But Z times X. So this time I've got to do it the other order. So I'm taking this column, that row, so that was 0. This column with this row, so that will be minus 1. This column with that row, so that's 1. And that one is 0. Okay, so you can see that it's different by a minus sign. So in this case, the commutator, so X comma Z, just the difference of these two matrices, just subtract this guy from that guy. So in this case, it's going to be minus 2, plus 2, 0.
So the commutator only exists when X and Z are both n by n matrix and they are the same size.
Sorry, what's the first thing that you said? That they're both?
they are both n by n matrix.
Oh, I see. Yeah. Yeah. So could you have different? Well, okay. So yeah, that's the normal way that we use it, because these matrices that we're dealing with are always square matrices, generally in quantum mechanics. So all the matrices are square. Maybe you could define it with you know, non-square matrices. But
I think, but
can you? Yeah.
if we want the like multiplication rule of a matrix to work, it has to be the same because like
Yeah.
it's like m times n matrix times like m times n matrix to make it times n like
Yeah. Yeah. I was thinking that maybe you could have some rectangular matrix here, but then that it would have to have the same dimension here when you invert it.
So they must be
then-
square matrix.
Yeah, and then okay, so I'm not sure of that. I'm not sure. It has to be square. I mean, so in quantum mechanics, often, well, all the examples that we normally deal with are square. Mathematically, maybe it can be extended, but I'm not sure. I'm not sure of that. But yeah, you know, it would have to be the same dimension here as well, right? So when you invert it, it has to be the same. Okay. All right. So, okay, so let's just do a quick quiz. So, all right, so find x Hermitian conjugate. So what would that be?
This is a real matrix, so it's just a transpose as.
So transpose of x. And transpose of x, in this case, what is that?
so
Just say.
Right, it's just the same, yeah. So this is an example of a matrix where the this Hermitian conjugate is actually the same matrix. Yeah. So that means x dagger is actually equal to x. How about y? Hermitian conjugate of y.
Still the same.
Right, yep, still the same, yeah. Because y, well, y star conjugate is this one. The minus signs get swapped. Then you transpose it, and then it's back to the same again. And what about z?
Same.
Yeah, also same. It's real, so conjugate does nothing, and then it's on the diagonal. Actually, yeah, these matrices just come up over and over, and we'll be encountering them a lot. These are so-called Pauli matrices, and they are kind of the sort of the fundamental matrices when you have like a two-dimensional space. Now, okay, what about commutator of x and y? So I did x and z here already. What would x and y give? conjugate. Yep. So getting 2i minus 2i 0, 0. Can we write that actually in terms of one of the matrices up there?
The 2i times z.
Yep. 2iz. Alright. So, actually, if you go up here, x commutator of z, you can also write this one in terms of that one up there. Should be 2i, no, minus 2i 1, so we've got I down at, yeah, that's right. So we found that x commutator z, or actually commutator, if we reverse the order of the commutator, it's actually the minus of it, okay? Because this is always true. You just put a minus sign in front of it, because if you put minus here, then it's minus st plus ts. So this is equal to 2iy, and we just found that xy was 2iz. So you might almost be able to guess the rule here. So the way that these commutators work is that you got x, y, z. It's like if you do x commutator with y, it's z with 2i. Z commutator with x gives y, and so y commutator with z gives 2ix. So they have this kind of cyclic property. Okay. I'm just throwing in some extra things here because I think you guys are pretty comfortable with this stuff. Okay. Oh, is that it? Oh, no, it's not. Right. And I think last lecture I mentioned something about eigenvectors, eigenvalues. Probably you have done this. Yes? Yeah. Okay. So eigenvectors, so normally you apply an operator to a vector and it becomes some other vector, right? It usually changes, of course, because it's, imagine it's as some matrix multiplication. Of course, it'll change the vector. But there's some special vectors where you apply the operator to it and it's kind of unchanged. And these are called eigenvectors. And the special thing here is that this vector here, we're calling lambda 1, is actually the same vector over here. And it's the same up to some kind of constant. So there's some constant value which so it's sort of proportional to the same vector. And this proportionality constant is called the eigenvalue, and these special vectors are called eigenvectors. Actually, it turns out that these things also are quite important in quantum mechanics. I'm not sure if we'll really go into a lot of detail about this so much, but for example, if you remember what I was talking about with the energy levels of an atom, so remember like those pretty neon tubes that I was showing you, and then how they have like some very special spectra that's coming off the atoms. So it turns out that those energy levels are actually it's basically the vectors, so you can actually work out what the frequency of the light coming off something is just by working out the eigenvectors of some matrix, which is determined by quantum mechanics, but it sort of comes into these things in terms of quantum mechanics pretty fundamentally. And kind of the reason why is because these energy levels are special states of the atom that are kind of unchanging. So in the case of these atoms, these actually what happens is that there are some certain states which are very stable in terms of the kind of time evolution of the system, and these turn out to be these energy levels. Okay, all right, but we'll come back to that maybe. And finally, it's a little bit like what we were talking about with the basis transformation stuff. I kind of brought it in there a bit earlier, so this is exactly what I was just talking about before. So if we have a vector alpha, then what we've been doing up until now is that we can write that vector in terms of some unit vectors E1 and 2 with some coefficients. But that was just some kind of arbitrary choice of how to represent this vector, because the way that you kind of tend to view these things is that the vector has some element of sort of reality to it, right? So the vector is kind of real, and then how you kind of look at it can be different. A bit in the same way, I can look at this pen, my head pointing this way or that way. It's still the same pen. It has some element of reality. It's just that I kind of perceive it in a different way, right? So the coordinate system is just how you represent it, and the vector is the actual real kind of has the reality of it, right? So I could represent my vector with these unit vectors. In that case, it'll have some coefficients like A1, A2, or I could represent it equally well in some other coordinate system, E1 dash, E2 dash, and of course it will have different coefficients because I'm looking at it with my head pointing somewhere else. But it's exactly the same vector, right? It's just representing it differently. And this coordinate choice is sort of arbitrary. Like I can just choose whatever that is according to my own convenience. Often the kind of thing that you might do in quantum mechanics is do these basis transformations, because what will turn out is that these vectors represent the state, and then I can represent that state in different ways. Okay, so another special type of operator, and this is a type of operator which actually induces this transformation between these two coordinates. Okay. So this is basically the transformation that links these two coordinates choices, right? So if I've got first coordinates E1, E2, I've got second coordinates E1 dash, E2 dash, then there's an operator which is has the property of being a so-called unitary operator, and this basically transforms all my unit vectors without the primes, E1, E2, into the ones with the primes. So it turns the red coordinates into the green coordinates. Okay? And so it basically, this operator will work for any of the unit vectors, and this is called a unitary operator because after all, these things, the ones in the green, they have to also be unit vectors, right? And if it changed the length of E1 to something longer than 1, then that's a problem because it's not a unit vector anymore. Also, it has to be a kind of a one-to-one kind of mapping. So it has to turn E1 into E1 prime, E2 into E2 prime. It can't just do something like turns E1 into E2 and E3, something like this. Like it has to be kind of one-to-one mapping. Otherwise, it's not a proper mapping of this coordinate system. So these are another special class of operators, and they have the special property that U dagger is actually equal to the inverse of U. So maybe have you done this? Unitary operators? Maybe not. Yeah. So so they have this special property of the Hermitian conjugate is actually equal to the inverse. So that's actually a pretty remarkable kind of property in a way, because normally calculating the inverse of a matrix, you've got to do something pretty complicated, right? And also like matrices, they're not guaranteed to have an inverse. For example, if they've got some zero eigenvalues, then it's not possible to invert that. But for these matrices, complex conjugate transpose actually is the inverse. Okay, all right. So let's just do a last kind of question here. So the first one, verify that vector there is the eigenvalue of x. We've got x is over here, but yeah. So, and then find its eigenvalue. The eigenvalue?
The eigenvalue is -1.
Yep, that's right. So basically this x thing, as you can see, it kind of swaps the elements, right? So x, so AB, do the matrix multiplication, you get BA, yeah? So if you swap the elements here, then this will be minus, that's plus, and the eigenvalue has to be -1. Number 2, what are the eigenvalues of Z just by inspection?
1 and -1.
Yeah, that's right. Yeah. So this is diagonal already, so it's actually really easy to see what the eigenvectors are. So in this case, the eigenvectors are just like 1, 0, and 0, 1. Okay, and then it's just the diagonal elements. And then finally, rewrite this thing in terms of this basis. Okay, so I just threw this question in at the last minute. What you need to do is to kind of transform this thing into the basis of E1 prime and E2 prime. So, okay, you guys are already working on it all. So, there'll be like 2 steps to this, okay? So, what you want to do is you want to actually first get a formula so that you can just substitute E1 into this. So this formula is kind of the wrong way around. Like if this was written in terms of E1 prime, all you have to do is just substitute that into there, and then that would be it. But then the first step would be you kind of have to invert this one, so that it's like E1 is equal to something E1 prime, something E2 prime. Okay, yeah, I'll give you a bit of a hint of how to do that. Let me just do the first one for you. So the best way to do this is basically like, I mean, you could kind of try and rearrange this, but the easiest way is just add these equations. That will cancel the E2 terms, right? And then you've got something on the left-hand side with E1 prime, E2 prime in terms of E1. Okay. And then for to get E1, equation for E1, you just subtract these 2 equations, and then you'll get some relationship in terms of E1 prime, E2 prime. Okay.
Is it 1/2 plus 1 I over 2, and the other is
1/2 plus I over 2. So, what are you saying? So you're saying lambda 2 half?
1/2, it's a vector, like the first 1/2 plus I over 2.
Oh,
And then the under it is the 1/2 minus I over 2.
okay.
Don't know if it's the correct answer, but
Okay. Let me just simplify this so that it looks I. What do you get?
Same.
Does it agree?
Yeah.
Oh, okay. Okay, alright. Fine, let me try it and see if I can verify your results. So E1, if we follow what I was just saying there, should be E1 prime plus E2 prime, and E2 should be E1 prime minus E2 prime. Then lambda 2 is 1 over 2, and basically the sum of those guys plus I. Yeah. So I think you guys are right. And sorry. And yeah, so you can actually do a little bit of simplification here because, 1 plus I over root 2 is e to the I pi over 4. This is e to the minus I pi over 4. Yeah. But, yeah. All right, good. Okay, so I think that's finally the end of preparation. Congratulations. Are you ready to do quantum mechanics?
Yes.
Okay, yes. Alright. Okay, so so the way I'm going to sort of teach this is actually not really an orthodox way of teaching quantum mechanics. Normally the way you teach quantum mechanics is you sort of start doing Schrödinger equations and all this type of thing, and then and eventually you kind of realize that all these things can be equally formulated in terms of vectors. But the way I'm going to do it is that I'm immediately going to view things in terms of vectors. Right? It's actually kind of easier, the maths is easier, and actually that's the way that anybody that is working in, say, quantum information, things like this is the way they view everything anyway. So you're immediately sort of jumping in, skipping over a whole bunch of stuff, and kind of starting at this point, but I think it's actually an easier starting point. So let's just compare what we're doing in terms of classical physics, just to get a little bit of a kind of an idea of the strategy of what we are trying to do here. So suppose you have a typical problem in classical physics where you're kicking a ball and it's like projectile motion. You kick a ball, flies off somewhere, and then the problem is like you want to predict where it's going to land, things like that. Classical kind of problem. So here, of course, I don't care about the actual ball and how to solve all that. But let's just talk a little bit about how we kind of strategize to solve this problem initially, right? So before you even solve Newton's equations, like what are you actually what is your approach of solving this problem? And basically, the kind of the thing that you boil down is that the only thing that's really important here is like the coordinates of the ball, right? So that's like the position of the ball and the speed of the ball. And all the other things like, the ball is like brown and it's like this shape and I'm going to kick it with my foot and I'm wearing sneakers on there. All these other things, you forget about all these other details, right? You boil it all down into just like four numbers basically. Just the position, well, I'm thinking like 2 dimensions here. So 4 numbers, 2 for the position and 2 for the velocity, right? And basically the kind of the structure of what you do to solve this is that you start with your kind of initial parameters which describe the system, initial position, initial velocity. Then there's some machinery of Newton's laws, blah, 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 blah. We don't care about that here. And then what all that does is that it allows you to get what the position and velocity is some later time. Okay? So basically what this is doing is that we are describing like the state of the ball, that's the thing that we're interested in, just with well, in this case, like say 2 vectors. Okay, so 2 vectors, x and b. And of course, so this will work in any dimensions, 3 dimensions or even 1. And as I just said, even though there's a lot of other complications in reality, actually you don't really have to worry about it, and you sort of all boil it down to these 4 numbers in this case. So the quantum mechanics, actually the strategy is quite similar, even though the formalism is very different. So that whole framework of we're going to have something to describe the state of the system, and then we're going to work out how that state changes in time. Actually, that's exactly the same in quantum mechanics. It's just that like equations are different, and also there's some other sort of assumptions that are different, as I'll go on and say. So kind of abstractly, this is what you do in quantum mechanics. You describe the state of an object by some vector. Okay. So this vector actually will, in the case of quantum mechanics, will be actually some complex numbers. So that's one difference already to classical physics. Our position and velocity, they were not complex numbers classically, but this is going to be in general complex. And what are these vectors here, 0, 1, 2? So these are some distinct states of the physical system. Okay? So the actual nature of the vector is actually quite different in quantum mechanics. Now you probably are thinking, okay, I don't understand what are these physical states. So let me give you a couple of examples of what these physical states actually are. So kind of a classic quantum problem is an atom. It's very small. It's a classic kind of application of quantum mechanics. And turns out, we don't actually solve it in this course, but it turns out that there are some discrete states of an atom as predicted by quantum mechanics. And so, for example, these different states of the atom could be these states that I was just mentioning. Okay? So 0 is like the lowest energy state of the atom. 1 is maybe the next most excited state, 2 is more excited states. Okay? And those states, it doesn't mean that an atom can only be in those states, actually. In fact, an atom can be in any one of those states. In fact, an atom could be, so if you write that the atom is in this state of A0 plus A1, what that basically means is that the atom is kind of partly in the lowest state and then also partly in the first excited state. And so basically, you're allowed to have sort of a little bit of the atom in one state, a little bit of the atom in some other state.
Question. So were you talking about the atom or the electrons surrounding the atom?
We're talking about the electrons, actually. Yeah.
Oh.
Yeah. The electron determines most of the property of the atom. The nucleus doesn't really do very much, actually. Well, at least for normal situation. I'm talking about it's like not in the sun or anything like that. Just like atoms which are floating around at regular temperatures. Okay, let me give you a couple more examples just so you can get a feel for what these states are. So at the beginning I talked about this kind of example. You had like these man-made structures where you have electrons that are going maybe left or right of the channel. So another kind of example of a state would be, say, if this electron goes left, that maybe let's call that 0, and if it goes right, let's call that 1. Okay. And according to quantum mechanics, well, it certainly can be in those two states. It could be definitely left, definitely right, but it can also be in some other combination of these two states. And then so the state where these are again some complex coefficients, the atom, oh sorry, I think I meant electron here. Electron. So the electron is partly in the left and the right channel. So that would mean that it's sort of kind of split and going left, going right at the same time. That is actually allowed in quantum mechanics. That's a valid type of state. Another example is Schrödinger's cat. So the cat is dead. That's one particular state of the cat. Or the cat is alive. That's another state. And quantum mechanics can have both. Can have both the cat is dead and alive at the same time, in principle. Practice is a bit hard.
I got a question. So, like, does A0 and A1 have to add up to 1, or it can be a little larger because they can happen at the same time?
No, it has to add up to 1, as in the modulus squared of these things have to add to 1. Yeah. The A0, because these are complex numbers actually. Yeah. So this has to add up to 1. So quantum mechanics is these things eventually are related to probabilities of measurements. So this is like before you open the box. Yeah. So before you open the box, it's in this state. When you open the box, then you measure that the cat's dead, then you would find it in that state with probability A0 squared. And yeah, that's right. And if you found it was alive, it would be with probability A1 squared. It has to be one of those two. So it has to be has to add up to 1. Okay, and if we sort of take quantum mechanics to the extreme, then some examples. This would be sort of again, this is like an example which is maybe difficult to see in practice, but exists in principle. Is so these, when you kick the ball, so we could say, okay, so the ball is at the top of the trajectory, let's call that 0. When it's over here, let's call that 1. Of course, all these other positions are all different states too, but I'll just pick 2. And, well, those are 2 different distinct states. So these also are allowed to be in some kind of superposition. And if you had some combination here, what that would be saying is that the ball is sort of simultaneously here and here at the same time. And that's also an allowed state of quantum mechanics. In practice, it's quite difficult to kind of see that, but it's allowed by the laws of quantum mechanics. Basically, it becomes harder and harder to see these types of states, the sort of the bigger things are. So for atoms, the first example that I showed you, that's pretty easy actually to see. But for this one, it's basically impossible to see. But in principle, it's possible. Well, it's allowed by quantum mechanics. So so if we compare classical and quantum physics, then basically these are kind of different in only kind of what you are allowed in terms of what you call a quantum state. Okay, so so basically one major difference in quantum mechanics is that superpositions are allowed in quantum physics, right? So what do I mean by that? So classically, this example is impossible. I can't have the ball here and here at the same time, right? So so classically, if we just limit it to those 2 states, okay, for state 0, which is at the top of the trajectory, or I can have it at the bottom. I can't have it both at the same time. That's, it's not possible. But quantum mechanically, you can have this more general state. So another way to kind of view this is that, well, quantum mechanics is sort of an extension of classical physics because, well, these two are just two particular parameter choices of this more general state, right? So clearly that is just A0 is 1 and A1 is 0. And clearly that is A0 is 0 and this is A1 is 1, right? So, quantum mechanics actually contains classical physics, but there's some extra states that you are allowed to kind of have, which you don't have in classical physics. So this is the sense in which quantum physics actually sort of contains classical physics, but there are some other things which you have to take into account, which is basically the superposition effect. Okay. Yeah, and this is the point Danny was raising, is that we also demand that whenever we have this general superposition state, these coefficients can be any complex numbers, but you need to have the norm of this vector equal to 1, right? Because, well, okay, it's just it's kind of a postulate actually. The norm of the vector has to be equal to 1. And the consequence of that is that the modular squared, sum of the modular squared of all these coefficients has to be equal to 1. Okay. And the reason for that underlying, that kind of postulate is that eventually it's going to be linked to probabilities, and these probabilities have to add to 1. Okay. All right. So maybe we'll finish up on this slide. So the simplest kind of quantum system is a quantum two-level system, or what's called a qubit. Okay. So actually, this is kind of what we were writing in the previous slides too. But here we've got just two levels, and we've got these coefficients alpha and beta, and again these are complex in general, but we need these parameters, the modular squared of these things, to add to 1. And a neat way to actually parameterize this, so if you think about it, two complex numbers actually has like 4 real numbers in it, right? So the real and imaginary parts of alpha and the real and imaginary parts of beta. Yeah. So of those 4 parameters, if we demand that they satisfy this, actually there's only 3 effective parameters. And it turns out that actually, even if you multiply this state by a phase, it doesn't actually change anything in quantum mechanics. So if you have a state psi, you could equally just multiply it by some phase e to the I phi. And actually it doesn't really, you can never observe this phase, and there's no physical consequence of this phase. Okay. Maybe we'll talk about that later, but basically of these 4 parameters, 1 goes away due to normalization, and then 1 is kind of this phase factor, but it doesn't do anything. So you basically only got 2 real parameters in this state. And these 2 parameters are theta and phi. And these are just written so that you can, that it satisfies this equation. and the complex factor is just stuck on here, because if you multiply it through by, this phase is different. I should have chosen a different example, different symbols. It's called chi. So if you multiply this by e to the I chi, it doesn't change anything. So essentially, I've chosen that phase here to be just like 1 here. And then you've just got these two parameters, theta and phi, and that actually parameterizes all the possible states that you can have on a two-level system.
Question: what is e to the power of I phi? Is it just so that it why is it here?
Why is it there? Well, because so alpha and beta can be so alpha, if I write it totally generally, I can write it in the polar decomposition. So let's call it like r and e to the I chi. Okay, just a general complex number. Yeah, and beta, let's say s e to the I phi. Okay, so this is another way of parameterizing complex numbers. You know, r, chi, s, and phi. So it's 4, right? But now I need alpha squared plus beta squared equal 1, right? Okay. And then, so that means that actually, if I just put in this parameterization, this phase always goes away with the modulus squared. So actually, this equation is equivalent to r squared plus s squared is 1.
Where did e's power go?
Oh, so yeah, so any number, so if I, so alpha modulus squared is alpha star. Okay. And then alpha is r e to the I chi, and then alpha star is r e to the minus I chi. And then these e to the I somethings, they always disappear, r squared. Yeah. And so basically for the r and s, I could equally write it because this looks like, cosine sine relation, right? So I could, let's call r cosine, well, theta over 2, s of sine theta over 2. Okay. And then if I write it like this, then this chi, actually, I can factorize that out of the whole thing. So I've got psi. So now let's write it in terms of our parameterization. E to the I chi, 0, sine theta with the I phi. Okay, so that's what we've got so far. And then let me factorize this out of this factor of e to the I chi. The cosine theta over 2 and sine. This will be e to the I phi minus chi. Oops. 1. Okay. And okay, it's not obvious at this point, but actually this is this global phase factor which actually never does anything. So what I'm going to do is I'm going to actually just throw it away because it never does anything physical. I'm just going to tell you that now because I don't think I can really explain it at this point. But this basically doesn't do anything, so I'm going to set it to 0. And then this is the extra parameter that's left. Okay, so maybe I shouldn't have called it phi. Okay, so phi minus chi, I'm going to call it phi. So
once I figure out how like to the I5 disappear, I'm good. I
Yeah.
understand.
Right. Great. Okay. Great. Then maybe because we've got Spring Festival and then it'll be 2 weeks. Maybe can I set both homework 3 and 4 to be handed in by Thursday of the week when we come back?
So 2 linear algebra homework.
Yes, there's just 2 linear algebras.
Yes.
Because we've done all the linear algebra now.
Mhm.
Yeah, I think
Yeah.
that's okay.
Okay. All right, great. And have you thought a little bit about assignments, or talk about that later? Yeah, we've gone over time, so we'll talk about that later.
Okay.